Hello, I'm Channa Bankapur. I'm going to discuss my solution to the LeetCode problem, search in rotated sorted array second. It's today's daily challenge in LeetCode. The problem definition is we have a rotated sorted array and we need to find a target in that, whether it is present or not. And it is rotated at some pivot, but it is not known to us beforehand. So, for example, if this is the sorted array, original sorted array, but we don't get to see that directly, what we get to see is this rotated version of it. So it is rotated at this pivot, the fifth element. That's how in the rotated version we have the last three elements in the beginning and then followed by the first four elements, right? So and given a target, so suppose in this example one they are given 0 is the target, 0 is present there, so that's why we should return true, but we need to find whether it is present or not. Suppose if target is 3, it is not present, so we need to return false, right? If you observed in the example, some elements could be repeated, not necessarily all of them are unique. Actually, that if all of them are unique, that would have been a little simpler version of this problem, and that is the first part of this problem. If you see the follow-up part here, they mentioned that this is a follow-up problem to search in rotated sorted array, and in that problem all of them are unique, right? So maybe it is better to discuss that and then see what are the challenges when we have some repeated elements. So let me show you that problem and discuss the solution to that. So this is rotated, the search in rotated sorted array problem, where all of them are unique. So that is actually mentioned in the follow-up here, the third constant here. The third constant says all values of nums are unique, right? So here we can apply binary search directly. So the way I'm going to apply binary search is, if you observe the example, so we have something like this 4, 5, 6, 7, and 0, 1, 2. Suppose if this is the array which is already rotated, suppose if the target is, let me take a different target, suppose if the target is 6, so then 6 is present here, but we know that because it is rotated, the first element is always greater than the last element, right? If it is rotated already. So that's how I can see that the target is present in the first part, right? If I call them as two parts where um, uh, the first part has all the larger elements and the second part has the smaller elements, because they should appear before in the sorted array, right? So because 6 is greater than or equal to the first element, it is present in the first part. What if the target is say 1? So because it is less than the first element, then it should be in the second part. So that we can easily figure out. But yeah, we don't know where it is split. So what we can do is we can come up with a predicate which is going to be true for all the values from this target onwards, right? Because if you see the binary search I'm going to use, which has this standard way of solving the problem, it is going to start with a range which with low and high here, and it always comes up with a predicate, and the predicate tells us whether we should reduce the high to mid or increase the low to mid plus 1, right? So that happens because of the predicate here. So the predicate has two parts. One is if the target is in the first part or second part. Knowing that, we can actually adjust the predicate. So if you observe the predicate here, um, so if you observe the predicate in this case, the way I have written is, if target is greater than or equal to the first element, that means it is in the first part. In that case, suppose 6 is that case, right? In this case, we need to have true for all of these and then false for these two, right? So how do we know that? If the mid is greater than or equal to, sorry, greater than or equal to the target, right? First of all, that is 6. Or if mid is lesser than the first, because lesser than the first are the second part of the array where all of them are lesser than this one, and we know target is not present there, so they are on the right side of it. So that's why this condition should help. If target is present in the second part, suppose if target is 1, then we need to have true true here and then false in all of these places. So now if you see, if the mid false on an element which is greater than or equal to the first element, that means it is in the first part, so all of them should be false. But if it is greater than the target, so what we need to have is the mid element should be greater than or equal to target for sure. Along with that, it should be lesser than the first element. That's how it is in this second part. So these two elements are going to satisfy that condition, right? So that is the predicate I'm coming up with. Otherwise, this is a standard binary search, right? So by the way, if you don't know the binary search I'm using, there are already three problems we have solved in LeetCode in daily challenges. The first one being on October 8th. So let's see, where is October 8th? Yeah, so in October 8th, if you see here, that was the first problem we solved, binary search problem. It's a classic binary search, but I already used this method. So please, go through that one. If you have solved that, and if you want to know a little more, on October 16th, we had another problem, which is pretty much binary search, just that it is given in two-dimensional form. But otherwise, if you flatten it into one-dimensional array, it is regular binary search on a sorted array, right? If you want to know more about binary search, there is one more problem here solved on November 6th. So if you see November 6th, where we wanted to find the smallest divisor given a threshold. So there actually there was no array, but we have an imagined sorted array, and then we applied binary search on that, right? So this will give you a better idea of how binary search works and what is the kind of binary search I'm talking about, right? So that's the same binary search I'm using it. The predicate itself is separated out as a function, so that should help us solve this problem in a simpler way. So this is going to work in just big of log n time, because if you see there, low and high are at the extreme end of the array to start with, and every time either high reduces to mid or low goes up to mid plus one. So the problem size is reduced by a factor of two, and this whole thing, this predicate function is still constant time function, right? So that's why this whole thing works in big of log n time, right? So this is for the first part of the first version of the problem. This is a simpler version. But what about the problem we have at hand here, right? Because not all of them are distinct. So if you observe, there is the only difficulty is if first and last element are kind of same. So the scenario could be is an even more complicated than this. Suppose we have like a million elements, and in that all most of pretty much all of them are just two 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 two, and there is some one hidden somewhere here, and then again two 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 two. So there are a million elements, and there is only one hidden. This one is hidden somewhere, and we are looking for whether it is one is present or not. How do we even know that? This is sorted array, obviously it is pivoted around this index, but how do we know that, right? So it's very hard to know. That means why it is hard is, if you have this as low and this as high, and suppose mid falls onto this one, and this is also two, and how do I know the one is present before this or after this, right? Because if it falls on here, I wouldn't know the difference, right? Because that's all we can see, mid element. So that is why in the worst case, this could take linear time, right? That's the problem here. So it might take linear time in cases like this. Uh, we don't even know that it is going. It's a smaller element. What if this is three, right? So we don't even know that one is present or not, right? Or what if all of them are two? That's also a case we don't even know. So that's why this is not a, we are not going to get a big of log n solution all the time. In some cases it could be linear, but the good news is, if the first and last elements are not same. Suppose we have suppose like we have two 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 here, but at some point we have one followed so maybe there are a few ones here, right? Or maybe let's take a little difficult example. Suppose we have 20 20 20 followed by, and then again we have a smaller element, say 1 1 1, and then again 5 10 like this, and then it stops. If you look at the first element and last element are different, so if they're different, obviously the first element has to be greater than the last because it is rotated. And in that case, whatever the target we are searching for, that can be now easy, right? Because if you're searching for a smaller element, we know that it is present, it could be present somewhere here, and a regular binary search can be applied, because the predicate, whatever we discussed earlier, is going to work on this one directly, right? If we are searching for an element which is greater than the target, we know that it is also going to work according to the same rule. Suppose if there is some 25 here, we should be able to search for 25 also, right? So that's why the only issue is, it's not just about repetition, as in repetition is not an issue. The issue is, if the first and last elements are same, we don't have a good way of doing it, right? So that's why what I have done is, let me show you my code directly, because we already seen the other part. Because I'm making sure the first and last element are different. So because of that, I handle these cases of n being 0 and then 1. If it is 0, obviously it is false. Whatever the target we are searching for is cannot be there. If the size is only 1 and so if whether the size is 1 or the first element itself is target, we are going to return true, right? So that's one case we are handling it, right? So after that, in this part, this is the part which might take linear time. So we are going to make sure the first and last elements are distinct. So what I'm going to do is I'm decreasing the last element. I is going to start with n minus 1, and then it keeps decreasing as long as the ith element is same as the first element, right, which is at 0. So I keep decreasing it, and so this might end up taking linear time overall. So if I reduces to 0, that means we don't have any distinct element, right? We are back to the first element. In that case, we're going to return false. That means target is not found. And if num0 is already the target, we already handled in line number 5 here. So that's why that is a case we don't have to worry. So we're going to return false. If not, then we have nums0, which is different. Some number set 50 in the beginning, and whatever I, which is essentially the last element for us, is going to be some number which is lesser than 50, say 40, something like this, right? So now we have something different, and now the repetition does not matter. So rest of the things are very similar to what we saw in the previous the other problem. So here I'm searching, the low is going to be 0, and I is I plus 1, because that's how we normally work with, right? I plus 1 is beyond here. If low is here and I is here. So if the target I'm searching is greater than this nums of I and lesser than nums of 0, we are going to get I plus 1 as the answer, right? So because of that, I'm having 0 and I plus 1. Otherwise, I'll search using this regular binary search here, and this part of the code is complete copy paste from whatever we have already seen in the other problem, right? So it's going to search for that element. So in the result, if result index is I plus 1, that means it is in that in between ith element and the first element, or whatever the index we have got is not equal to the target, that means we missed it, and that means it is not present, and we're going to return false. Otherwise, we return true. In that case, it is present at that index res. All right. So that's the idea here. So this works in linear time only in one particular case. Otherwise, it works in log n time in most cases. See, it is working here. Let me show you the running time of this one. How much time it took. So it is much better. It took 8 milliseconds and it is 87 percentile. That means it is in a good shape, right? So we cannot get much better than something like this, right? So otherwise, the time complexity, it's clearly in the worst case it is linear time because of the while loop between line number 9 to 11. But if the last element, if we find one element which is different from the first element, so it's essentially if zeroth index is whatever the element is, this is the first element nums of 0, and there is some element which is lesser than nums of 0 here. So whatever the point we are going to find in this case, and if all of these after that are equal to nums of 0, so this size, the number of elements which are equal to nums of 0 at the end of it, at the trailing end of the array, is what is going to be linear, right? Other than that, we take log n of this size. If this size is k and this size is n minus k, so we are going to take n minus k plus log k time, right? So this is the time complexity we have, right? Strictly speaking, it is linear time, but in most cases, or on an average, it works really, really fast, right? That's how we got a very good running time, all right? So let me know, there are different ways of approaching this problem. Let me know if you have a different approach in the comments below. Otherwise, make sure you go through some of the binary search problems we have solved earlier, right? If you like the video, make sure you click on like button there, and also subscribe to the channel. Yeah, keep solving a problem every day, and thanks for watching.